Hello calculus students. In this video we're going to take a look at our 5.7, 5.8 notes. We're going to be looking at integrals that involve the natural logarithm and also inverse trig functions. So let's start by reviewing the log rule for integration that you have seen before, which says the following: the integral of 1 over x dx, remember the power rule didn't work in this case, was equal to the natural log of the absolute value of x plus c. Now, if we have a function u that is a differentiable function of x, then we can rewrite this property in terms of u. It would look like this: the integral of 1 over u du equals the natural log of the absolute value of u plus c. Okay, now, since the derivative of u with respect to x, which is actually u prime, since du dx equals u prime, then we can write the following. We can write that if I multiply both sides of this equation by dx, then we can write that du is equal to u prime dx. All right, so therefore, if we take that property, the integral of 1 over u du, we can rewrite that, but I'm going to make a replacement. I'm going to take this du, and I'm going to replace it with u prime dx. All right, so the integral would look like this: the integral of u prime over u dx, and that is equal to the natural log of the absolute value of u plus c. Okay, so in other words, all that to say, when you're looking at an integral of a ratio, try and find patterns where the denominator is a function u, it's a function, a differentiable function of x, and the numerator is the derivative of that denominator. When that's the case, then it's very simple integral. It's just the natural log of that denominator plus the natural log of the absolute value of that denominator plus c. So for example, let's take a look at example number 1. Okay. So let's take a look at example number 1, where our denominator is x to the 6th minus 1. If we were to, let's call that u. Okay, so we're going to call this denominator, we're going to call it u. Well, if you take the derivative of x to the 6th minus 1, you're going to get 6x to the 5th. So the numerator is u prime. So it fits this pattern. We have the integral of u prime over u dx. So the integral then is just simply going to be the natural log of u. Remember, u was that denominator, the natural log of the absolute value of u plus c. So this integral is simply the natural log of the absolute value of that denominator, x to the 6th minus 1, and then plus c. All right, let's take a look at example 2. In example 2, the denominator is x to the 3rd plus x. Now, if you take, let's call that our u. Okay, so that's u. Now, what would u prime be then? If we take the derivative of that denominator, we're going to get this exact numerator, 3x squared plus 1. So that's our u prime. This is u prime. So that fits the pattern of that u prime over u. So the integral is simply the natural log of the absolute value of the denominator, which is x to the 3rd plus x, and then plus c. All right, then let's take a look at example 3 and see if it fits that pattern as well. Let's let the denominator, let's call the denominator u. Well, if you take the derivative of tangent x, its derivative is secant squared x. So we have, again, u prime over u. So our integral then would just be the natural log of the denominator, the natural log of the absolute value of the denominator, which would be tangent x, and then plus c. All right, so always be on the lookout for that u prime over u pattern, because when you find it, it's going to be very simple. So now let's take a look at some other examples that aren't, unfortunately, they're not quite so simple. They don't just always fit into u prime over u. If you look at this example number 4, the denominator is 2x, and the derivative of 2x is 2, which is not the numerator. So in this case, let's go back to using good old u substitution. So let's go ahead and choose that denominator u, to be u. Let's let u be 2x. Then du would be 2dx. Okay, so if I were to rewrite this integral in terms of u, I'm going to replace the 2x with u. But dx, I can't just do a straight up substitution because du is equal to 2 times dx. So remember, the way we balance that out, I can replace dx with du as long as I balance it out by putting a factor of 1/2 in front of the integral. So we'll write 1/2 the integral of 1 over u du. So then it goes back to our log rule. The integral of 1 over u du is the natural log of the absolute value of u plus c. So this would be 1/2 the natural log of the absolute value of u plus c. And then let's go back and back substitute. Remember, u was 2x. So this would be the natural log of the absolute value of 2x plus c. All right, and then example 5, let's take a look at that. So again, this doesn't quite fit u prime over u. So let's go ahead and use regular u substitution. So we're going to let u be the denominator, 4x minus 1. Then du would be 4 dx. All right, so we'll replace 4x minus 1 with u, and then we can't just replace dx with du because du is 4 times dx. So to balance that out, we'll put a factor of 1/4 out in front of our integral. So it would be 1/4 the integral of 1 over u du. All right, and so that integral is 1/4 the natural log of the absolute value of u plus c. And then last but not least, let's do our back substitution. Let's replace u with 4x minus 1. So it'd be the natural log of the absolute value of 4x minus 1 plus c. All right, and then example 6. All right, in example 6, let's let u be the denominator again. So we're going to let u be x squared plus 2x. Then du would be 2x plus 2 du. All right, I mean dx. Whoops, let me fix that. Du is 2x plus 2 dx. All right. Okay, so now as we go to make substitutions, we're going to replace x squared plus 2x. This will be replaced by u. And then we can't quite replace x plus 1 dx with du because du, there's a factor of 2 we need to take care of. In fact, we could rewrite this du as 2 times parentheses x plus 1 dx. So now we can see that trying to replace x plus 1 dx with du doesn't quite work because du is 2 times that amount. So what we're going to do to balance that out is put a 1/2 out in front of the integral. So that would be 1/2 the integral of 1 over u du. All right, and so the integral of 1 over u du is the natural log of the absolute value of u plus c. And then substituting the x squared plus 2x back in for u, we'd have 1/2 the natural log of the absolute value of x squared plus 2x and then plus c. All right, and then number 7, let's take a look at that one. Again, let's let the denominator be our u. So we're going to let u equal 3x plus 2. Then du would be 3 dx. All right, so we'll replace the 3x plus 2 with u, but I can't quite replace 1 times dx with du because du is equal to, it's equal to 3 times dx. So to balance that out, we'll put a 1/3 out in front of the integral. So we'll have 1/3 the integral of 1 over u du, which is 1/3 the natural log of the absolute value of u plus c. And then our final answer then would be the natural log of the absolute value of 3x plus 2 and then plus c. Okay, then number 8, why don't we, number 8, let's let u be this part, just this part of the denominator, natural log of x. So we're going to let u be the natural log of x. Then du, remember the derivative of the natural log of x is 1 over x dx. So that works out nicely because we can replace the natural log of x, that will be u, and then this 1 over x dx, all of that can be replaced with du. So we can rewrite this whole integral then as the integral of, whoops, I'm going to do that in blue, the integral of 1 over u du, which, using our log rule for integration, is just the natural, the natural log of the absolute value of u plus c. And so now when we go back and back substitute, replace u with what's equal to natural log of x, our final answer will be the natural log of the absolute value of the natural log of x plus c. All right, and then this next example, the problem says, find the area of the region bounded by the graph of y equals x over x squared plus 1, the x-axis, and the line x equals 3. So you should have seen enough of these examples by now that you realize we're really being asked to find a definite integral. We're being asked to find the definite integral from, well, let's see, from 0 to 3 of the function x over x squared plus 1 dx. All right, so now let's see if we can use u substitution to do that. It doesn't fit the pattern of u prime over u, so let's go ahead and do regular u substitution where we let u be the denominator, x squared plus 1, then du would be 2x dx. All right, so we'll replace x squared plus 1 will be u. Now we can't quite replace x dx with du because du is equal to 2 times dx. So we're going to have to put a factor of 1/2 out in front to balance that out. So it would be 1/2 the integral from 0 to 3 of 1 over u du, or 1/2 the natural log of the absolute value of u. Now this is a definite integral, so we'll use the first fundamental theorem of calculus to evaluate that antiderivative from 0 to 3. But first let's go back and back substitute. Let's replace u with x squared plus 1. All right, so now that's going to be equal to 1/2. And we're integrating from 0 to 3. So let's start by replacing x with 3. So we'd have the natural log of the absolute value of 3 squared plus 1 minus the natural log of the absolute value of 0 squared plus 1. And then simplifying a little bit, we'd have 1/2 times. Now, since 3 squared plus 1 is definitely going to be positive, we can drop that natural log, not the natural log, we can drop the absolute value symbol and just call this the natural log of 4. And then, oops, I didn't want to close those parentheses. Let me erase that. And then minus, let's see, this would be minus the natural log. And again, 0 squared plus 1 is positive 1. We don't need the absolute value sign, so we can just leave it there. And then I wonder if you caught my arithmetic mistake. 3 squared plus 1 is not 4. 3 squared is 9. So this would be 9 plus 1, which is 10. And then we could simplify that just a little bit more, because you might recall that the natural log of 1 is 0. So we could write our final answer as 1/2 the natural log of 10. So now let's take a look at this table of the integrals of the 6 basic trig functions. Now you're already familiar with a couple of these, integral of sine and integral of cosine, and actually those are really the two that you need to make sure that you have memorized. Most likely, those would be the ones you'll come into contact with on the AP exam. But it's good to know that there are integrals for all 6 trig functions. So I just wanted you to take a look at them, and then let's just work a couple of problems where we have to use these integrals of basic trig functions to integrate. So our example number 10 says the following. It's a definite integral. We're going to take the integral from 0 to pi fourths of the square root of 1 plus tan squared x dx. So the first thing we can do is actually simplify this quite a bit, because you might recall from your pre-calculus course that the trig identity 1 plus tangent squared x, is equal to secant squared x. So let's rewrite this integral as the integral from 0 to pi fourths of the square root of, I'm going to replace that 1 plus tan squared x with secant squared x dx. And then we can simplify a little bit more, because we're taking the square root of secant squared. So those two functions will undo each other. So we can rewrite this as the integral from 0 to pi fourths of just secant squared, no, not secant squared, duh. We just took the square root of secant squared, so it would be secant x dx. Okay, so look up at the table and let's see what the integral of secant of a function is. Well, it's going to be the natural log of the absolute value of secant of that function plus tangent of that function plus c. So let's go ahead and integrate. So this would be the natural log of the absolute value of secant x plus tangent x, and then we're going to evaluate that from 0 to pi fourths. All right, so let's go ahead and do that. I'm going to first replace x with pi fourths, so we'd have the natural log of the absolute value of secant pi fourths plus tangent pi fourths. All right, we'll simplify that in just a minute. And then minus the natural log of the absolute value of secant of 0 plus tangent 0. All right, and then simplifying that, let's see. That would be the natural log of, now secant of pi fourths and tangent of pi fourths are both going to be positive, so we can drop the absolute value sign. And let's recall that secant of pi fourths is the reciprocal of cosine, or secant is the reciprocal of cosine, so we can take the cosine of pi fourths and then flip that over. So let me just kind of do this over here to the side. Let's see. When we take this, remember this cosine of pi fourths is the square root of 2 over 2, but we're going to flip that over, and that would give us 2 over the square root of 2, and then rationalizing, we would get 2 square root of 2 all over 2, and then those 2's will cancel. So all that to say, the secant of pi fourths is just the square root of 2. So this would be square root of 2 plus tangent of pi fourths. Remember, pi fourths is where x and y are the same, and tangent is y over x, so that's just going to be 1. All right? Then minus the natural log of secant of 0 is remember, secant is a reciprocal of cosine. Cosine of 0 is 1, and so the reciprocal of 1 is 1. And then tangent of 0, remember at 0, okay, at 0, your coordinates there are 1, 0. And remember, tangent is y over x, so we have 0 over x, so tangent of 0 is just 0. Okay, and then we'll just simplify this a tiny bit more and write our final answer as the natural log of the square root of 2 plus 1 minus the natural log of 1. Oh, and the natural log of 1 is 0. So we can just leave our answer as the natural log of square root of 2 plus 1. So let me draw a box around that, and we're done. All right, so let's now take a look at example 11. Example 11 says, find the average value of f of x equals tangent x over this closed interval from 0 to pi fourths. So remember, to find average value, we're going to take a portion of the integral of tangent x from 0 to pi fourths, and that portion will be 1 over pi fourths minus 0. So in other words, we're going to take 1 divided by pi fourths minus 0 of the integral from 0 to pi fourths of tangent x dx. All right, so that would be, well, first of all, 1 divided by pi fourths. Remember, when you divide by a fraction, it's the same thing as multiplying by a reciprocal. So that would be the same thing as 4 over pi, okay, times, now, what is the integral of tangent x? Well, let's go back and look at our chart. The integral of tangent x is the opposite of the natural log of the absolute value of cosine of our function plus c. Whew. Okay, so let's go ahead and do that. So the integral of tangent x then is the opposite of the natural log of the absolute value of cosine x, and then we'll evaluate that from 0 to pi fourths. All right, so that's going to be 4 over pi times, well, let's first replace, oops, I'm missing an x, aren't I? Oops, let me see if I can fix that. I have to erase a little bit. This should be the cosine of x. Oops. Cosine of x. There we go. And then let me squeeze in the rest, that right side of the absolute value symbol. Okay, so the first thing we're going to do is we're going to replace x with pi fourths. So we would have negative natural log of cosine of pi fourths. Well, cosine of pi fourths is square root of 2 over 2. And then minus, let's replace x with 0. And then remember, we're subtracting a negative natural log of x. So I'm going to change that negative sign to a plus sign. So it'd be plus the natural log of the cosine of 0. And cosine of 0 is 1. Okay? So then we can simplify this a little bit more. First of all, natural log of 1 is 0. And then the other thing I'm going to do is I'm going to take this negative and pull it out in front. So our final answer would be negative 4 over pi times the natural log of the square root of 2 over 2. Alrighty, and then let's go ahead and finish up by looking at these integrals. The integrals involving inverse trig functions. Now, we're not taking the integral of a inverse trig function. We're just going to look at some integrands that when you take the integral, the answer is an inverse trig function. Now, again, these look kind of crazy, and don't worry about too much. Probably the ones you're going to run into, if any, would be the one involving arcsine and the one involving arctan. But we're going to do an example of all three just so you have the exposure of them. So here's what we're going to look at. Let's let u be a differentiable function of x, and a is some constant bigger than 0. Then, if you see an integrand that looks like this, now the du is written here, but it could be written over here and replace that with 1. If you have 1 over the square root of a constant squared minus a function squared, then that integral is going to be arcsine, or sine inverse of u over a, your function over a plus c. If your integrand looks like this, the du could be over here. So if you have 1 over a squared plus a function squared, that integral is 1 over a times tangent inverse of u over a plus c. And if you have an integral or an integrand that looks like this, 1 over u times the square root of u squared minus a squared, then the integral is 1 over a of secant inverse of the absolute value of u over a plus c. So these get a little crazy. All right, let's try some examples. Let's take a look at example number 12. So which of these does this fit? Example number 12 seems to fit the pattern of number 1 up here, because if you look at this denominator, we have the square root of 4 minus x squared, And 4, as you know, would be 2 squared. So let's just go ahead and rewrite this integral as the integral of dx over the square root of, instead of 4, I'm going to write it as 2 squared minus x squared. So that means that 2 would be the a, and x takes the place of u. So using pattern number 1 up here, then the integral is going to be arcsine or sine inverse of u over a. In this case, that would be x over, our a is 2, so this would be the arcsine or sine inverse of u over a, or let's replace u with x and a with 2, so that would be arcsine of x over 2 plus c, and that's all there is to it. Okay, and then number 13, let's go ahead, we're going to simplify this problem just a little bit. I'm going to take out the 9, so let's just call that, just mark that 9 out and just call it 2 plus x squared. So 13 then looks awfully close to the pattern of number 2, where we have a squared, we have the sum of 2 perfect squares. Well, this doesn't quite look like that, but if we rewrite it, let's rewrite, remember this 2 we could think of as the square root of 2 squared. So let's just rewrite it like that. So it'd be the integral of dx over the square root of 2 squared plus x squared. So that means in this example, the square root of 2 would be the a, and then u is x. So this is going to be the integral. Here, let's go ahead and look at that pattern again. We're gonna write 1 over a. 1 over a arctangent or tan inverse of u over a plus c. We're just going to replace both of these a's with the square root of 2 and replace u with x. So our final answer would look like this. The integral of, sorry about that, the integral of 1 over a, and remember a is the square root of 2, so 1 over the square root of 2 times, why do I have the integral? I'm taking the integral, so let me erase that. Sorry about that. So our final answer is 1 over a, 1 over the square root of 2, and then times arctangent or tangent inverse of u over a, and we're going to replace u with x, and a is the square root of 2, and then don't forget your plus c. Okay, so you'll get a chance to practice a few more of these in your homework. If you have any questions, be sure and ask me in class, and I will see you then.